Welcome back. In this short video lecture, we are going to describe how to diagonalize a square matrix of order 2 by 2 and order 3 by 3. And I hope it will be useful to you. Please, before you watch the video, if you have not subscribed to my YouTube channel, please just press the subscribe button so that you can always get updates on all the lectures that will be posted on the channel. So let's go direct into the solution of the problem. So diagonalization of a square matrix simply means that you need to find a matrix P such that if you get the P inverse of that matrix, you multiply by A and then multiply by the P itself, then you'll get a diagonal matrix. But one thing that you have to remember is that not all square matrices can be diagonalizable. So I'll illustrate some few examples, 2 examples to be specific. So diagonalize the matrix. Actually, let me call this one an appetizer because a simple example. So appetizer. So A given by 2 minus 12 and then 1 minus 5. So in this matrix, in this question, I will explain all the steps required for you to do when you are working out diagonalization of a square matrix. So usually the first step is to find eigenvalues. Step 1 is to find eigenvalues. So remember, you find eigenvalues by solving this equation. So determinant of A minus lambda I equals to 0. So we'll have determinant of 2 minus lambda minus 12, 1 minus 5 equals to 0, which will give us 2 minus lambda minus 5 minus lambda. Then actually this will be plus 12. Plus 12 equals to 0. So we'll have minus 10 and then minus 2 lambda and then plus 5 lambda and then plus lambda squared plus 12 equals to 0. So this will be lambda squared plus 3 lambda and then plus 2 equals to 0. So product here is 3, sum, product is 2, sum is 3. So numbers will be 2 and 1. So I'll have lambda squared plus lambda plus 2 lambda plus 2 equals to 0. So doing the pairing, we'll have lambda into lambda plus 1 plus 2 lambda plus 1 equals to 0. Which tells us that lambda plus 1 times lambda plus 2 equals to 0. So this tells us that lambda equals to negative 1 and lambda equals to minus 2. So you can call this one lambda 1, call this one lambda 2, but there's nothing special. You can actually change the order. This can be 2, this can be 1. So that's step 1, eigenvalues. Step 2, eigenvectors. So for lambda 1 equals to -1, we need to solve this equation. So this being our matrix being of size 2 by 2, then our eigenvectors will be of this form. So therefore we'll have 2 minus 12, 1 minus 5 multiplied by x1, x2 equals to -1, x1, x2. So that we'll have 2x1 minus 12x2 equals to minus x1. So call this one equation 1. And then x1 minus 5x2 equals to minus x2, call it equation 2. So from equation 2, x1 equals to minus x2 plus 5x2, which will be 4x2. So that tells us that x1 equals to 4x2. So x2 is a free variable. So let x2 to be t, where t is any real number. So that means that vector v1 will be x1, x2. I remember by saying x2 equals to t, you mean x1 equals to 4t. So this will give us 4t and then t, which is just the same as 4 and then 1t. For it to be an eigenvector, then you'll remove the possibility of having a zero vector. So pick any real number that's not 0. But then fixing or setting t equals to 1, then v1, which we call the basis eigenvector, will be 4, 1. And then for lambda 2, which is minus 2, from our calculation, we'll also have a v2 equals to lambda 2 v2. Still, v2 will also be of the form x1, x2. So we'll have 2 minus 12, 1 minus 5 multiplied by x1, x2 equals to minus 2, x1, x2. So from this, we get the system of linear equations. So we'll have 2x1 minus 12x2 equals to minus 2x1. Call this one equation 1. And then x1 minus 5x2 equals to minus 2x2. Call this one equation 2. And then from equation 2, we have x1 equals to minus 2x2 plus 5x2, which will be 3x2. So this means x1 equals to 3x2. So x2 is free variable. So let x2 to be t, which is just a real number. And then this will tell us that x1 equals to 3t. So therefore v2 will be given by x1, x2, which will be x1 you put 3t x2 you put t, and then so this will be 3, 1, and then times t. But to remove possibility of having a zero vector, then we say t is any non-zero real number. So setting this t to be 1, then our basis eigen vector will be 3, 1. So that's step 2, finding the eigen vectors. Step 3 is to find this matrix P, which is actually formed by the eigenvectors you obtain in step 2, and it is formed by actually the columns of P are the values of the eigenvectors. So our V1 was given by 4, 1, 4, 1, and then our V2 from our calculation in the previous step is 3, 1. So 3, 1. So this is how we form P, just for a matrix formed by the columns, where columns are the eigen vectors. So step 4 is to find P inverse. Step 4 is to find the P inverse. So these are 2 by 2 matrix. So P inverse will be simply given by, so determinant will be 4 times 1 minus, so we'll have 1 over determinant of P, and then this being a 2 by 2, so we interchange the elements along the main diagonal, and then change the sign of elements in the lead in their secondary diagonal. So determinant of P, 4 times 1, 4 minus 3, which is 1, so just be P inverse will be 1 over 1, 1 minus 3 minus 1, 4. So just 1 minus 3 minus 1, 4. And then step 5, which is the last step, show that P inverse AP equals to D. So we'll have P inverse is 1 minus 3 minus 1, 4. Our matrix A was given by 2 minus 12, then 1 minus 5. And then P itself was given by 4, 1, 3, 1. So this one equals to what? So let's start by doing the multiplication, say at this point. So we'll have 1 minus 3 minus 1, 4, and then into, so 2 by this one is 4, 4 minus 12, this is 8 minus 12 is minus 4, 2 by this is 6, 6 minus this will give us minus 6, 4 minus this is minus 1, and then 3 minus 5 minus 2. 1 times this minus 4 plus 3 is minus 1. Minus 6 plus 6 is 0. 4 minus 4 is 0. 6 minus 8 is minus 2. And indeed, this is a diagonal matrix whose elements along the main diagonal are the eigen values obtained in the first case. So that is how we find and we do diagonalization of a square matrix. So the first step is to find eigenvalues, find eigenvectors, and then form the matrix P, which is simply a matrix obtained by columns formed by the eigenvectors in that order you have found them. And then once you have found that matrix P, you find the inverse of the matrix P, and then show that P inverse AP equals to D. So in a similar manner, you can also work out this, diagonalize this matrix A given by 1, 1, minus 3, and then minus 1, 3, and then 1, minus 1, 1, minus 1. So if you work out correctly, you'll find that eigenvalues are lambda 1 equals to 2, lambda 2 equals to minus 2, and lambda 3 equals to 3. And then the corresponding eigenvectors, if you work out, you will find that V1 will be given by minus 1, 0, 1. V2 will be given by 1, minus 1, 4. And V3 will be given by minus 1, 1, 1. So which tells you that your P, if this is the case, will be given by minus 1, 0, 1, 1, minus 1, 4, and then minus 1, 1, 1. And then next step, you'll find P inverse. So when you do the correct calculation, the P inverse for this matrix will be minus 1, 1 over 5, 1 over 5, and then minus 1, 0, 1, 0, 1 over 5, and then 1 over 5. And check that P inverse AP is equals to D, where your D for this case will be given by 2, 0, 0, 0, minus 2, 0, 0, 0, 3. And one thing that I have to remind you is that there's nothing special with this ordering. So remember, you can as well call this negative 2, you can call it your lambda 1. So the way you order your eigenvalues is what determines how your P will look like. Another person could have labeled this one as lambda 1 to be negative 2, lambda 2 to be to be 2, and then say lambda 3 to be 2 to be 3. If this is your labeling, then this eigen vectors will actually vary. So you have this one will be a V2, and then this one will be a V1, and then this one will be a V3. So the structure of your P will change because the first column will be formed by 1, minus 4, minus 1, 1, minus 1, 4. Second column will be formed by minus 1, 0, 1. Third column will be formed by minus 1, 1, 1. So it tells you that the inverse will be different from what we have here. And when you do the correct thing, P inverse AP will be a diagonal matrix, but then now the order of the elements will be that V here will have now negative 2, 0, 0, 0, 2, 0, and then 0, 0, 3. So this is how your diagonal matrix will look like. Or another person who says, let me call lambda 1 to be 3, lambda 2 to be 2, and lambda 3 to be -2, there's nothing special. You can as well give this order, but then remember that what you get as your P will be different from this matrix we have here. And also your diagonal matrix will be different from what we have in these cases here. If you work out the correct thing, then the order of if this is the ordering, then the diagonal matrix will be 3, 0, 0, 0, 2, 0, 0, 0, -2. So the order in which you are finding your eigenvalues and you are labeled your eigenvalues and eigen vectors determine the structure of what you call the P matrix, and also determine the order in which the eigenvalues will be arranged in the diagonal of the final matrix defined as D. So thank you, and do as many examples on the same. But if you have more questions, don't hesitate. You can reach me through 254 705 050 158 for any further clarifications or any other questions. Or you can send me an email at vcnando@gmail.com. So that's the end.